When we've been working with normal distribution, we've been working specifically where we had a sample size of 1. In other words, we were working to find the probability of getting a single value. What happens when we are interested in a group of values, or perhaps more like an average of values? To that end, we're going to start looking at samples with a sample size greater than 1, so n will be greater than 1, and our z-score value is going to be changing slightly. And we're going to be working with the normal distribution. So when we have a sample size greater than 1, our formula changes from z equals x minus mu over sigma to z equals x bar, which is our sample average minus our mean. This is where it gets really a little bit different, is our standard deviation divided by the square root of n. So essentially it's the same z-score, but when we take an average and we went from x to x bar, essentially we added up a bunch of x's and divided by n to get an x bar. And to make that same adjustment with our standard deviation, we have to divide by the square root of n. Now, what's interesting about that is our error term diminishes as we increase our sample size, because this is clearly smaller than that as we increase our sample size. So increasing the sample size decreases the amount of variation that we have. So when we are working with the distribution of sample means, and this is what we call this, because we're no longer working with x's, we're working with the means. So this is the distribution of sample means. Our mean will always be the mean. So the mean will always be the mean, but the standard deviation will now change to the standard deviation divided by the square root of n. All right. So consider the distribution of IQs. In this case, the mean of the IQs happens to be 100, and the standard deviation is 15. Well, if we have that, essentially, there's 1 standard deviation below, 2 standard deviations, 3 standard deviations below. So instead of being this, our mean is still at 100, but this would be 1 standard deviation above would be 115, and this would be 85. This would be 130, and this would be 70. And this would be 55, and this would be 145. And all we did was say, okay, for singular values, 68% of the singular values are between 85 and 115, and 68% of the IQs are between 85 and 115. 95% of the IQs are between 70 and 130, and then 99.7 of the IQs are between 55 and 145. So that's if we were looking at an individual. Where does an individual? My IQ is between 130 and 145. Well, if it's up here at 130, then I'm in the 95% group. Okay. So what happens though, instead of working for an individual value, we start working with means. Well, we call the distribution of sample means, and our standard deviation is now no longer just the standard deviation, it's the standard deviation to square root of n. So we're going to take a sample of size 25. So here was our original standard deviation of 15, and we're going to divide by the square root of 25. Well, 15 divided by 5 is 3. So I would say, hey, my standard deviation of x bar, of the sample means, that's what this means. This standard deviation of the sample means, that's that little x bar means, is 3. So now, where we used to have a 15, we're spreading by 3s. So 68% would be, our mean is still our mean, and that's really nice. The mean doesn't change, but this is 103, and this is 97. So 68% are between 97 and 103, where previously 68% were between 85 and 115. So this is for our sample means. So this is having a sample, if we had samples of size 25. And then we'd have this is 106 versus 94, and this is 109, and this is 91. As you can see, standard deviation, even though we still had the same initial population standard deviation, when we increased the sample size, it got narrower. So our variation diminished. So basically, the main thing to understand is the population standard deviation didn't change, it's still 15, but the standard deviation of the sample means, or the distribution of the means, has a smaller spread because we divide by the square root of n. Okay, so continuing on. So when do we get to use this? Well, if the underlying is normal, the distribution of sample means is always normal. By the way, that's really important. So when the underlying distribution is normal, then the distribution of the sample means is normal, regardless of the sample size. We don't have to have a big sample size, because in a moment, we're going to have to talk about that. Unfortunately, not all distributions are normal. What if the distribution is highly skewed, or has some other shape, is bimodal, etc.? Well, we have a solution, and that is known as the central limit theorem. And the central limit theorem basically states that the sampling distribution of the expected values, in other words, the distribution of the means of a population with a mean of mu and a standard deviation of sigma, will always be approximately normal for any population, regardless of the shape of the population, if the sample is large enough. So basically, central limit theorem says, you know what? Doesn't matter what the underlying population looks like, it's normal if the sample size is large enough. And when we're working with the distribution of means, we define large enough as being 30 or larger. In other words, greater than or equal to 30, right? So if n is greater than or equal to 30, we can say it's normal by central limit theorem, even if the underlying population is not normal. Once again, the mean is still the mean, and the standard deviation will always follow. When we're talking about means, the standard deviation of the mean was always the standard deviation divided by the square root of n, if n is 30 or larger. Understand, the underlying distribution is not changing. So for the underlying distribution, the mean is still the mean, but the standard deviation is still the standard deviation. But the mean of the x bars is just x bar, the sample mean, and the standard deviation of x bar is the standard deviation divided by the square root of n. So once again, underlying distribution, the mean is the mean, and the population mean is the population mean. But the distribution of the sample means follows central limit theorem, or actually always follows this: the mean of the x bar equals the sample means, and the standard deviation of the x bar is the standard deviation of the population of the square root of n. This is always true for every mean, but it's actually normal. It's actually normal if the sample size is 30 or larger. Do not confuse law of large numbers with central limit theorem. Law of large numbers says as we increase the number of trials, the percentage of successes moves closer to the number of successes. In other words, closer to the theoretical value. All right. Central limit theorem just says the population, the distribution of the means is normal. All right. Distribution of the means is normal if the sample size is large enough. Okay. So this deals with normality. This deals with moving towards the theoretical. We've already stated that the sampling distribution of sample means is approximately normal with mean mu and standard deviation sigma divided by the square root of n. You're going to need to memorize that. And the conditions necessary to use sample means. We need a simple random sample. The population must be normal, or n must be greater than 30. A lot of times we don't know if the population is normal, but if our sample size is greater than 30, the standard deviation of the population must be known. All right. And if that's the case, if it's known, then we have the standard deviation of x bar, the sample means, is the standard deviation divided by the square root of n. Okay. All right, so that's an introduction to the central limit theorem and the distribution of sample means. In the next video, we will work some